Hi guys, welcome to our video lesson for the weekend. It's called Finding Inverses of Exponential and Logarithmic Functions. So if you remember, we had a lot of fun in class on Friday talking about what logs were. So these were our notes on Friday. And basically we learned that logs are the inverses of exponential functions because we could use them to solve exponential functions. We can also use exponential functions to solve logs. So inverses are things that undo each other. So for instance, when we are evaluating all these logs here in example 2, we thought of them in exponential form to really undo. Okay, so basically, if you understand that the inverse of a log is an exponential and the inverse of an exponential is a log, this should make a little more sense to you today. Okay, so our learning target is I can find the inverses of exponential and logarithmic functions. An exponential function, such as f of x equals 2 to the x, accepts the values of the exponents as inputs. So what that means is we plug in values into the exponent, right, where the x is, and delivers the corresponding powers of 2. So that's what we're doing. We're taking 2 to the power of x as the outputs. Okay, so basically the powers of 2 are what are going to be where f of x is. So just as one example, we could say 4 equals 2 to the second, where 2 is your input and then 4 is your output. All right. The inverse of f of x equals 2 to the x is f inverse of x equals log base 2 of x. So yesterday in our lesson, we talked about how the base always remains the same. So the base in an exponential, in this case, is 2. That's what's being taken to the power. And so that is all the base in the log. So it should be pretty simple to find inverses just based on that simple fact. But the base remains the same. You just write it in either exponential or log form. Now, recall that the domain and range of a function are reversed. So I just want to underline that. Domain and range are reversed when finding the inverse. So they switch, okay? So f inverse of x equals log base 2 of x accepts the powers of 2 as its inputs and delivers the corresponding exponents as its outputs. So when I would write my example from above in log form, now that 4 that was the output is going to be my input. So it would be log base 2 of 4, okay? And that is 2. So let me come here, change my color. So this 2 that was the input became my output, all right? And this 4 that was the output became my input. So hopefully that makes sense after going through our logs in our class activity. Okay, we're going to discover what the graph of a log function looks like, knowing what we know about inverse functions. So it says graph f inverse of x equals log base 2 of x given the graph of f of x equals 2 of x shown. Recall that the graph of a function's inverse is its reflection over the line y equals x. So we did inverses last semester with linear, quadratic, and cubic. And so hopefully that kind of rings a bell. The graphs, we just switched the x and y coordinates because the domain and range switched. And the graph happened to be the reflection over the line y equals x, which I have graphed lightly here on my graph as the dotted line. If you see this here, I'm just gonna put some yellow on it. So that's the line y equals x. Okay, so I first want to just review f of x equals 2 to the x. We've taken a quiz over exponentials, but let's talk about all of its attributes and then look at this table here on the left. Okay, f of x equals 2 to the x is graphed already. So this is my f of x right here. And the table is filled out. So when I put negative 2 in, so 2 to the negative second, I got out 0.25. We like fractions. That's 1/4, right? Because 2 squared is 4, but because it's negative, you do the reciprocal. Similarly, 2 to the negative 1/2, 2 to the negative first is 0.5, which is 1/2. And then 2 to the 0 is 1. Anything to the power of 0 is 1. And then, so hopefully this is ringing a bell. and we can continue. So this was the thought process as this table was being filled out. We're just taking powers of 2. So the inputs go into your exponent, the outputs were corresponding powers of 2. And then the graph is shown over here. Let's review the attributes of an exponential function. Remember, the asymptote is a horizontal asymptote. So I want to write that specifically. And it's at y equals 0. So I'm going to be plotting this one in blue over here. This should be review for us. We know that an exponential function has a horizontal asymptote at the k value. So if it's been shifted up or down, it'll change from 0. But this is just a parent graph. Okay, because of the arrows on both ends of our curve, we know we can put any x value we want into the function. So the domain was all real x values, which we used an inequality. Negative infinity is less than x, which is less than positive infinity. The range is directly related to our asymptote. Since our graph is entirely above that asymptote at y equals 0, it's all y values greater than 0, and we just wrote y is greater than 0. Okay, our end behavior. For end behavior, remember, we go to both ends with our x values as x approaches positive infinity. Remember, that's to the right side of your graph. F of x, or I'm going to write y, that's fine. Our y values also approach, as we see the arrow is going up to their positive infinity. And then as we go the other way, as x approaches negative infinity, which is to the left side of our graph, our y values are approach our asymptote at 0. Okay, so let's get to graphing the inverse, which is our log graph, and see how the attributes are similar but different. Okay, f inverse of x equals log base 2 of x. So the easiest way to graph an inverse is just to reverse the domain and range. So we're switching the x and y values. So basically, I'm going to take this column of outputs and make it the inputs. And I'm going to use fractions. So I'm going to put 1/4, 1/2, 1, 2, 4, 8. And so what I'm doing there, and we could fill this out without even using the table before us. We know that first one I'm finding log base 2 of 1/4, and we know that that's -2. The second one I'm finding log base 2 of 1/2. We know that's -1. Log base 2 of 1, 2 to the 0 is 1, etc. So I'm finding log base 2 of 2, that's 1. Log base 2 of 4, that's 2. Log base 2 of 8, that's 3. So as we see this second column, our outputs were our inputs in the other one. So they just switched. So when I graph those over here on the same graph, I'm going to go 1/4 or 0.25, -2, 1/2, -1, 1, 0, 2, 1, 4, 2, 8, 3. And I'm going to graph this. Now, when I graph this, when it's coming downward, I am not crossing that y-axis. Ooh, this is really shaky. Sorry about that. I'm not crossing the y-axis for the reason that I actually have an asymptote there. So when on my exponential function, I had a horizontal asymptote at y equals 0. When we do the reflection and do the inverse, we now have a vertical asymptote at x equals 0. So we have a vertical line as our asymptote. So we have to be careful there. Now, our domain, because we have this vertical asymptote, our graph is entirely to the right of x values of 0. So we have all x values greater than 0. So we just write that as x is greater than 0. Our range, however, look at this. Now I have an arrow going down and then it's growing forever up. So now my range is all real y values. So now my range is negative infinity is less than y, which is less than positive infinity. And finally, my end behavior is actually a little different. The first way, as x approaches positive infinity, my y values are also approaching positive infinity. If we look at our right side of our graph, the arrow is going up. It's never going to stop increasing. But I actually cannot say for my other end, I can't say as x approaches negative infinity because x does not approach negative infinity. We have that asymptote at x equals 0, and so it stops my x values from decreasing. So what we have to do here, so I'm going to put a star here because this is different. As x approaches 0, and then we're going to put a little plus sign as a superscript, which I'll write what that means. That means from the right. So that means I'm coming into 0. I'm moving in the leftward direction, but I'm coming in from the right side. So that's how we would describe that. If my graph was on the other side of the asymptote, I could be approaching 0 from the left side. So as x approaches 0 from the right, we see that our y values are getting infinitely small. So y approaches negative infinity. So with this, I want to show you some cool things. We know these are the inverses of one another. And we know that means that the domain and range switch. So take a look at your domain and range right now. The domain of my exponential was infinite. It was all x values. And now look at my range of my log. Now that's my range. So that should make sense because my x and y switched. Similarly, you can see that the range of your exponential was y is greater than 0. Hey, now that's our domain in our log with x values. X values are greater than 0. Okay, with that also, our horizontal asymptote changed to a vertical asymptote. So y equals 0 now is x equals 0. And then our end behavior also switched. So the end behavior, the first one as x approaches positive infinity, y approaches positive infinity, those switch, but they're both positive, so you can't really tell. However, as x approaches negative infinity, y approaches 0, those reversed, right? They switched over here. See, now as x approaches 0, y approaches negative infinity. So just some cool things to point out. Big thing is we're going to be graphing these log functions someday, actually after this lesson that we do in class. So tomorrow in class, we're going to be doing finding inverses algebraically. But it's important that you remember these things about the log graph and how they are related to the exponential because they're inverses. And gosh, math is just so fun. Okay, guys, I hope you have a great weekend, a long weekend, and I'll see you on Tuesday.